Tonight, we follow the story of the Oort Cloud, the silent boundary at the edge of our solar system. Welcome to the Orbit for Sleep channel. Let us follow the orbit of science and drift gently towards sleep. At the farthest edge of the sun's influence, far beyond the last recognized planets, the solar system does not end with a clean boundary. Its outer limit fades gradually into a vast, cold halo of ancient debris. This region is known as the Oort Cloud. It remains invisible to telescopes, yet its effects quietly reach the inner solar system over immense spans of time. For most of human history, the sky appeared stable and predictable. Stars held steady positions, and wandering lights followed familiar paths. Then, from time to time, a new object appeared without warning. A long, pale tail stretched across the night. These long-period comets returned only once within many human lifetimes. Their orbits could not be explained by the known planets alone. In the 20th century, astronomers studied these unusually shaped trajectories with increasing precision. Jan Oort analyzed their paths and recognized a pattern that suggested a distant reservoir of icy bodies surrounding the solar system. The idea proposed that trillions of frozen objects were stored far beyond the planets, held loosely by the sun's gravity. The Oort Cloud was not detected by light, but inferred through motion. The scale of this region is difficult to grasp in ordinary terms. The outer boundary is estimated to lie a significant fraction of the distance to the nearest stars. Light from the sun would require many months to reach this zone if it traveled at the speed of modern spacecraft. In everyday terms, it can be compared to a city surrounded not by suburbs, but by a dim, spherical wilderness stretching far beyond visible maps. The objects within the Oort Cloud are remnants from the early formation of the solar system. During the period when the giant planets formed, gravitational forces scattered vast numbers of icy fragments outward. Some escaped into interstellar space. Others slowed and became trapped in distant orbits. Over time, these fragments settled into a vast, spherical distribution, rather than a flat disk. Occasionally, the calm structure of the Oort Cloud is disturbed. The slow passage of a nearby star or the gentle tidal pull of the Milky Way alters the balance of gravity. A small number of frozen bodies are nudged inward and begin a long fall toward the sun. As they warm, their ice turns directly into gas, forming the luminous tails seen from Earth. The existence of the Oort Cloud reveals that the solar system is not defined only by its visible planets. It is shaped by invisible populations, slow gravitational motion, and distances that exceed ordinary perception. The familiar region of Earth and its neighboring planets occupies only a tiny central zone within a much larger, unseen structure. The Oort Cloud is not a physical cloud in the way weather forms in Earth's atmosphere. It is a vast, etherical region of space, filled with countless icy bodies that surround the solar system at extreme distances. These objects are composed mainly of frozen water, carbon dioxide, methane, and ammonia, preserved from the earliest stages of planetary formation. The term describes a gravitational boundary rather than a visible structure. Individual objects within the Oort Cloud are separated by enormous distances. Even though their total number is estimated to be in the trillions, collisions between them are extremely rare. Each body follows a slow, elongated orbit around the sun, held only weakly by gravity at the edge of its reach. The Oort Cloud differs fundamentally from the familiar regions of the solar system. The planets, asteroid belt, and Kuiper belt all lie within a relatively flat disk shaped by the rotation of the original solar nebula. The Oort Cloud, by contrast, forms a spherical shell. This shape reflects the way its objects were scattered by gravitational interactions with the giant planets and later influenced by passing stars and the Milky Way itself. In practical terms, the Oort Cloud functions as a long-term storage zone for comet material. Its icy fragments remain frozen in deep space for billions of years, largely unchanged. Only a small fraction are ever redirected toward the inner solar system, where they become visible as long-period comets. An everyday comparison can be made to a quiet warehouse located far outside a city. The city center represents the planets and the Sunday. The warehouse holds ancient materials that are rarely accessed. Most of the time, it remains undisturbed and unnoticed. Only during rare events do a few stored objects return to active use. The Oort Cloud, though unseen, is therefore a fundamental part of the solar system's true structure. It preserves the physical memory of the system's formation and quietly shapes the long-term behavior of comets that occasionally visit the visible skies of Earth. The region known as the Oort Cloud begins far beyond the orbit of the outermost planets and extends outward to distances that approach the gravitational boundary between the Sun and nearby stars. Its inner edge is estimated to start tens of thousands of times farther from the Sun than Earth is. Its outer edge reaches a significant fraction of the distance to the nearest stellar neighbors. These distances are best understood through comparison. Light from the Sun reaches Earth in about 8 minutes. From the inner boundary of the Oort Cloud, sunlight would require many months to arrive. From its outermost edge, the journey would stretch into years. Even the fastest spacecraft humans have built would need many thousands of years to reach this region. The extent of the Oort Cloud is determined not by visibility, but by gravity. The Sun's gravitational influence weakens gradually with distance. At extreme ranges, the pull of nearby stars and the overall gravitational field of the Milky Way begin to compete with it. The outer limit of the Oort Cloud marks the zone where the Sun's control becomes fragile and intermittent. The inner portion of the Oort Cloud is thought to be more densely populated, with objects that remain more consistently bound to the Sunday. The outer portion is more loosely held and more easily disturbed by passing stars. This layered structure reflects the long history of gravitational reshaping that has acted on the solar system since its early formation. An everyday analogy can be made to the influence of a lighthouse along a distant coastline. Close to the shore, the light is strong and consistent. Farther out, the beam grows faint and unreliable, easily overwhelmed by other lights. In the same way, the Sun's gravitational presence fades gradually into a region where external forces increasingly dominate. The Oort Cloud, therefore, does not have a sharp physical edge. Its beginning and end are defined by gradual changes in gravitational balance rather than by solid boundaries. This vast transitional region marks the true spatial scale of the solar system as a structure embedded within the larger environment of the galaxy. The existence of the Oort Cloud is closely tied to the violent early history of the solar system. In its first stages of formation, the the sun was surrounded by a thick disk of gas, dust, and ice. Within this disk, the planets gradually assembled through countless collisions and mergers of smaller bodies. As the giant planets grew, their gravity became powerful enough to reshape the entire outer solar system. Large numbers of icy fragments were repeatedly disturbed by close encounters with Jupiter, Saturn, Uranus, and Neptune. Some of these objects fell inward toward the Sun. Others were flung outward at high speed. Most escaped completely into interstellar space. A smaller but significant fraction slowed enough to remain weakly bound to the sun at extreme distances. Over long periods of time, these scattered objects formed a vast spherical population rather than a flat disk. This shape emerged because repeated gravitational nudges from passing stars and the slow tidal force of the Milky Way altered their orbits in every direction. The result was a distant shell of debris surrounding the solar system from all sides. In this way, the Oort Cloud exists, not because it was deliberately formed, but because it is the natural byproduct of planetary construction. It represents material that was neither incorporated into planets nor fully lost to interstellar space. It is a long-term gravitational archive of the solar system's earliest rearrangements. A familiar comparison can be made to dust created during large-scale construction within a city. Most material becomes part of finished buildings. Some is cleared away completely. A small portion drifts outward and settles in remote areas, where it remains undisturbed for long periods. The Oort Cloud is comparable to this distant accumulation of leftover material on a cosmic scale. The presence of the Oort Cloud therefore reflects the balance between growth and loss that shaped the solar system. It exists because early gravitational forces were strong enough to scatter material outward, yet not always strong enough to remove it entirely from the sun's domain. The Oort Cloud has never been observed directly through a telescope. Its objects are too small, too dark, and too distant to reflect enough sunlight for direct imaging. Its existence is known through indirect evidence drawn from the behavior of long-period comets. When astronomers began carefully measuring the paths of these comets in the 20th century, a consistent pattern appeared. Their orbits were extremely elongated and arrived from all directions of the sky, not confined to the flat plane where the planets orbit. This spherical distribution indicated that their source could not be located in the known planetary region. The energies of these comet orbits provided further clues. Many arrived with just enough speed to reach the inner solar system once, then returned to deep space for tens of thousands or millions of years. Others were slightly accelerated and escaped the sun's gravity entirely after passing through the planetary region. These motion patterns matched the predictions of a distant, weakly bound reservoir. Gravitational physics allows the location of this reservoir to be estimated even without direct observation. By calculating how much energy a comet gains or loses during its passage near the planets, astronomers can reconstruct how loosely it was bound to the sun before entering the inner solar system. These reconstructions consistently place the source far beyond the Kuiper Belt, in the region identified as the Oort Cloud. An everyday comparison can be made to hearing footsteps in a dark building without seeing the person directly. The direction, speed, and echo of the sound reveal where the person must be located, even though the source itself remains hidden. In the same way, the Oort Cloud is mapped through the motion it produces rather than through direct light. The study of stellar motion also supports this conclusion. Computer simulations show that passing stars and the tidal field of the Milky Way can disturb distant comet reservoirs at precisely the distances predicted for the Oort Cloud. The consistency between observation, calculation, and simulation forms the foundation of our knowledge of this hidden structure. The Oort Cloud is therefore known not through sight, but through gravitational evidence written into the paths of ancient ice that occasionally enters the inner solar system. The Oort Cloud is not a single uniform layer of objects. It is understood as a broad structure with at least two distinct regions, commonly described as the inner Oort Cloud and the outer Oort Cloud. These regions differ in how tightly their objects remain bound to the Sun and how easily they are disturbed by external forces. The inner Oort Cloud is believed to lie closer to the Sun and to contain objects that remain more securely attached to its gravitational influence. These bodies follow extremely long but relatively stable orbits that can take hundreds of thousands of years to complete. Because they are less affected by passing stars, they act as a more permanent storage zone for ancient comet material. The outer Oort Cloud extends much farther into space, approaching the limit where the gravity of nearby stars and the Milky Way itself begins to compete with the Sun's pull. Objects in this outer region are only weakly bound. Small gravitational disturbances can alter their path significantly, sending some inward toward the planetary region or ejecting them completely into interstellar space. The difference between the two regions reflects the balance of gravitational forces over vast distances. Close to the Sun, gravity behaves like a steady anchor. Farther away, it becomes fragile and easily disrupted. This gradual transition creates a layered structure rather than a sharply defined border. An everyday comparison can be made to items stored on shelves at different heights in a lightly shaking building. Objects on the lower shelves remain undisturbed, held securely in place. Objects on the highest shelves are far more likely to slide or fall with even small vibrations. The inner and outer Oort Cloud function in a similar way under the influence of external gravitational motion. This internal structure helps explain why some long-period comets appear to originate from more stable, repeating source regions, while others arrive on paths that suggest recent and sudden disturbance. The layered nature of the Oort Cloud preserves both the long-term quiet history of the solar system and its ongoing interaction with the surrounding galaxy. The objects that populate the Oort Cloud are small, ancient, and dominated by ice rather than rock. They are commonly described as icy bodies, composed primarily of frozen water, carbon dioxide, methane, and ammonia mixed with dust and complex organic material. These substances condensed in the cold outer regions of the early solar system. Most of these bodies are only a few kilometers across. They contain little internal heat and receive almost no energy from the distant sun. As a result, their physical state has remained largely unchanged since the era of planetary formation. They function as deep freeze samples of the original material from which the solar system emerged. These icy objects differ from asteroids found closer to the Sunday. Asteroids are dominated by rock and metal and formed in warmer regions. The Oort Cloud bodies formed where temperatures were low enough for volatile substances to remain solid. This difference in composition explains why long-period comets produce large clouds of gas and dust when they enter the inner solar system. When one of these frozen bodies is redirected inward, its surface begins to warm as sunlight increases. Ice does not melt under these conditions. It changes directly from solid to gas in a process known as sublimation. The escaping gas carries dust with it, forming the visible coma and tail that characterize a comet. An everyday comparison can be made to dry ice used in laboratory demonstrations. Dry ice transforms directly from solid carbon dioxide into gas without becoming liquid. In a similar way, the frozen materials of a comet turn directly into vapor as they approach the sun, creating motion and structure from a body that was previously silent and inactive. The enormous population of these icy bodies means that the Oort cloud contains far more total mass in comet material than the visible comet population ever suggests. Only a tiny fraction of these objects are ever observed from Earth. Most remain permanently hidden in deep space, preserving the chemistry and physical conditions of the early solar system. Through these frozen remnants, the Oort cloud serves as a physical archive of the solar system's most distant and least altered material, recording a stage of planetary history that the inner regions no longer retain. Gravity is the primary force that gives the Oort cloud its overall shape and long-term stability. At the immense distances where this structure exists, gravity is weak, yet it remains the organizing influence that determines whether an icy body stays bound to the sun or escapes into interstellar space. Near the planets, gravity produces fast, tightly curved orbits within a flat disk. In the Oort cloud, gravity operates under very different conditions. The sun's pull is faint and easily influenced by additional forces. Over long timescales, small gravitational nudges accumulate and reshape the distribution of objects in all directions, producing a spherical rather than a flattened structure. The Milky Way itself contributes to this shaping process. As the solar system moves through the galaxy, it experiences a slow, uneven, gravitational pull known as a galactic tide. This tide gently stretches and compresses distant comet orbits over millions of years. Although the effect is subtle at any given moment, its cumulative influence becomes significant across the history of the solar system. Passing stars provide another important gravitational influence. When a star travels near the solar system, even at vast distances, its gravity can slightly alter the paths of Oort cloud objects. Some are pulled inward toward the sunday, others are pushed outward and lost permanently to interstellar space. These events are rare on human timescales, but frequent over astronomical time. An everyday comparison can be made to slow currents in a large lake. A single ripple appears insignificant. Over time, however, continuous, gentle motion reshapes the distribution of floating material across the entire surface. In the same way, weak gravitational forces gradually sculpt the overall form of the Oort cloud. The combined influence of solar gravity, galactic tides, and passing stars produces a dynamic structure that is both stable and slowly evolving. The Oort cloud is therefore not a static shell of frozen debris. It is a living gravitational system whose shape records the long interaction between the solar system and its surrounding galactic environment. The Oort cloud exists in a region of space where the sun's gravitational hold is fragile. Because of this, passing stars play a significant role in shaping the long-term behavior of its icy objects. Even when a star passes at a distance measured in trillions of kilometers, its gravity can still produce measurable effects. As the solar system moves through the Milky Way, it regularly encounters other stars at varying distances. Most pass far enough away to cause only minor disturbances. Over millions of years, however, these small gravitational encounters accumulate. Each close passage slightly alters the orbits of some Oort Cloud objects, gently reshuffling their long, slow trajectories. When a star passes unusually close, the effects are stronger. Some icy bodies may be pulled inward toward the sun on new paths. Others may be pushed outward and escape the solar system entirely. These stellar encounters act as one of the primary mechanisms that convert distant, inactive Oort Cloud objects into visible, long-period comets. The influence of passing stars also explains why the Oort Cloud maintains a roughly spherical shape. Stellar approaches occur from many different directions in space. Over long periods of time, this random pattern of external gravity distributes objects evenly in all directions rather than along a single plane. An everyday comparison can be made to pedestrians walking past a loosely stacked display of lightweight objects. Most people pass without noticeable effect. An occasional close movement sends one item sliding out of place. Over time, the arrangement gradually changes, even though no single person causes dramatic disruption. Astronomical models show that the current population of long-period comets observed near Earth is consistent with the expected rate of stellar disturbances acting on the Oort Cloud. The observed inflow of comets matches the pace predicted by these slow, distant encounters. Through the quiet but persistent influence of passing stars, the Oort Cloud remains connected to the wider movements of the galaxy. Its structure reflects not only the history of the solar system itself, but also the broader stellar environment through which it travels. Long-period comets originate primarily from the distant reservoir of icy bodies known as the Oort Cloud. These comets follow highly elongated orbits that can take tens of thousands or even millions of years to complete a single journey around the Sun. Most of the time, the icy objects that become long-period comets remain motionless in deep space. Their orbits are vast, slow, and stable under the Sun's weak gravitational influence. A small disturbance, often caused by the gravitational pull of a passing star or the tidal force of the Milky Way, can alter this balance. When such a shift occurs, one of these frozen bodies begins a long inward fall toward the inner solar system. As the comet approaches the Sun, its energy increases steadily. Sunlight warms its surface, and frozen gases begin to transform directly into vapor through sublimation. This escaping gas lifts dust from the surface, forming a bright cloud around the nucleus known as a coma. Solar radiation pressure and the solar wind then stretch this material outward into a long, glowing tail. The extreme length of long-period comet orbits means that most of them are first-time visitors to the inner solar system. Unlike short-period comets that return on predictable schedules, these bodies may not revisit the Sun for many human civilizations. Some will never return at all after their initial passage. An everyday comparison can be made to a package stored in a distant warehouse that is rarely accessed. Most remain untouched for generations. Only under special circumstances does one item return to active circulation, briefly appearing in the center of activity before being stored again or permanently removed. The study of long-period comets provides one of the most direct observational windows into the composition of the Oort Cloud. Each visiting comet carries pristine material from the earliest stages of solar system formation, delivered temporarily into the region where it can be measured and analyzed. Through this continuous but sporadic supply of distant visitors, the Oort Cloud remains quietly connected, the visible solar system. Its role as the birthplace of long-period comets allows scientists to probe a region that otherwise lies beyond direct observation. The Oort Cloud influences Earth through the slow delivery of long-period comets toward the inner solar system. These movements occur when the delicate gravitational balance that holds distant icy bodies is disturbed by external forces, such as passing stars and the tidal pull of the Milky Way. Once an object is nudged from its distant orbit, it begins a gradual inward descent that can take thousands of years. During most of this journey, it remains invisible and inactive. Only when it approaches the region of the planets does sunlight become strong enough to transform its frozen surface into gas and dust, revealing the object as a comet. The trajectory of a long-period comet is highly sensitive to planetary gravity. As it passes through the inner solar system for the first time, close encounters with the giant planets can significantly alter its path. Some comets are deflected back toward the Oort Cloud on new orbits. Others are redirected into shorter, repeatable paths. A portion gain enough energy to escape the solar system entirely after a single visit. Over geological timescales, this steady but irregular delivery of comets has affected Earth's environment. Impacts from long-period comets have contributed to the reshaping of the planet's surface and, in rare cases, produced global environmental effects. These collisions are infrequent on human timescales, but significant across the history of the Earth. An everyday comparison can be made to a distant reservoir releasing water through narrow, unpredictable channels. Most of the time, the flow is quiet and unnoticed. At rare intervals, a sudden surge reaches the central area, leaving lasting physical marks before the system returns to calm. Modern astronomical surveys now track many incoming long-period comets years before they approach the inner solar system. This allows scientists to study their composition, speed, and structure in advance. Each observation provides new data about the conditions of the distant Oort Cloud. Through this slow and indirect process, the Oort Cloud maintains a quiet, persistent connection with Earth. Its distant gravitational mechanics occasionally translate into visible motion in the night sky and, over vast timescales, into physical interaction with the planet itself. The history of Earth includes a long record of impacts from objects that originated far beyond the planetary region. Long-period comets, which trace their source to the Oort Cloud, have contributed intermittently to this history over hundreds of millions of years. These impacts differ from those produced by asteroids in both frequency and speed. Long-period comets typically approach the inner solar system on steep, high-energy paths. Because their orbits originate from extreme distances, their velocities near Earth are often significantly higher than those of most asteroids. When collisions occur, the amount of energy released is correspondingly large. Geological evidence preserved in Earth's surface records a number of major impact events. Large circular craters, shocked minerals, and global layers of unusual chemical elements testify to moments when extraterrestrial objects struck the planet. While many of these impacts were likely caused by asteroids, a portion is consistent with the dynamics of long-period comet collisions. Over deep time, such impacts have altered the course of Earth's environment. Some collisions triggered regional devastation. Others may have driven global climate change by injecting dust and vapor into the atmosphere. These intermittent disruptions formed part of the broader process through which Earth's surface and biological conditions evolved. An everyday comparison can be made to rare but powerful storms that shape a landscape over generations. Most days are calm and leave little trace. Occasionally, a single extreme event Increasing attention was given to the role of extraterrestrial impacts in mass extinction events. While asteroid impacts receive the most direct evidence, researchers continue to study the contribution of distant cometary sources linked to the Oort Cloud. Computer models show that disturbances in the Oort Cloud can produce temporary increases in impact rates at Earth. The Oort Cloud therefore forms part of Earth's deep environmental history, not through constant interaction, but through rare, high-energy encounters. These distant origins occasionally leave permanent signatures on the planet's surface and biological timeline. The icy bodies stored within the Oort Cloud contain not only frozen water, but also a wide range of carbon-based compounds. These substances formed in the cold outer regions of the early solar system, where temperatures were low enough for volatile molecules to remain solid for billions of years. When long-period comets from the Oort Cloud enter the inner solar system, they carry this ancient material with them. As sunlight warms their surfaces, water ice and frozen gases sublimate into vapor, releasing both simple and complex molecules into space. Astronomical observations have identified carbon monoxide, methane, ammonia, and a variety of organic compounds within cometary comae. Laboratory analysis of comet-like material and space mission samples has strengthened this connection. Spacecraft studies of comet composition show that many of these molecules closely resemble the chemical ingredients required for basic biological processes. These findings support the idea that early Earth may have received part of its water and organic material through repeated comet impacts. During the early history of the solar system, Earth experienced a heavy bombardment of both asteroids and comets. At that time, much of the planet's surface water may not yet have been fully established. Repeated impacts from distant icy bodies could have delivered significant quantities of water and organic compounds to the growing oceans. An everyday comparison can be made to the gradual filling of a reservoir by many small deliveries rather than a single large supply. Each individual delivery appears minor, but over long periods, the total contribution becomes substantial. In a similar way, countless small cometary impacts may have contributed meaningfully to Earth's early chemical inventory. Modern astronomical research continues to refine this picture by comparing the isotopic composition of comet water with that of Earth's oceans. Some measurements show close similarity, while others reveal differences. These mixed results indicate that comets likely contributed part but not all, of Earth's water supply. Through these chemical connections, the Oort Cloud is linked not only to the physical history of Earth, but also to the deeper story of how the ingredients for life may have been distributed throughout the early solar system. For most of human history, long-period comets appeared without warning in skies that were otherwise stable and predictable. Because their return cycles exceeded many human lifespans, each appearance was experienced as a unique and unrepeatable event. These sudden visitors left lasting impressions on early observers across different cultures. Ancient astronomical records from Asia, the Middle East, and Europe contain careful descriptions of bright comets with extended tails that persisted for weeks or months. These records often aligned with long-period comet behavior rather than with the predictable orbits of short-period comets. Although the physical origin of these objects was unknown at the time, their motions were observed and documented with remarkable precision. Without scientific context, early civilizations interpreted these rare events through cultural and symbolic frameworks. Comets were often associated with major social changes, natural disasters, or shifts in political power. Their unexpected arrival and slow retreat across the sky gave them an air of significance distinct from ordinary celestial motion. Over time, systematic observation gradually replaced symbolic interpretation. By the late stages of pre-modern astronomy, scholars began to recognize that comets followed physical paths through space rather than divine or purely symbolic trajectories. This shift laid part of the groundwork for later scientific investigations into their true origins. An everyday comparison can be made to a long-forgotten traveler who appears briefly in a quiet town and then disappears again for generations. The visit leaves stories, drawings, and memories that persist long after the traveler is gone. In a similar way, long-period comets left enduring marks in historical records long before their distant source was understood. In the modern scientific framework, these ancient observations are now recognized as early human encounters with material originating from the Oort Cloud. The records preserved by past civilizations provide indirect confirmation that long-period comets have been interacting with the inner solar system for thousands of years. Through these cultural and historical imprints, the Oort Cloud extends its influence beyond physics and geology into the long development of human observation, interpretation, and record-keeping of the natural world. For much of scientific history, the solar system was thought to end near the orbit of the most distant known planet. Beyond that region, space was assumed to be largely empty. This view began to change as long-period comets challenged existing models of planetary motion. The recognition that these comets originated from far beyond the planetary region forced a major expansion of the conceptual boundaries of the solar system. The proposal of the Oort Cloud in the 20th century transformed the solar system from a compact planetary neighborhood into a structure with a vast, invisible outer domain. This realization altered how scientists understood the scale of the sun's gravitational influence. The solar system was no longer defined only by planets and their flat orbital disk. It became understood as a layered system extending tens of thousands of times farther into space, with a hidden spherical population of icy bodies surrounding the visible planets. The Oort Cloud also reshaped theories of planetary formation. It demonstrated that the early solar system was a violent, dynamic environment in which material was constantly scattered, redistributed, and sometimes preserved in distant reservoirs. The present calm of the planetary orbits is therefore understood as the end result of a much more chaotic beginning. An everyday comparison can be made to the discovery that a familiar city contains vast underground infrastructure unseen from the surface. Streets, buildings, and daily activity appear to define the city. Only later does it become clear that an enormous hidden network supports and extends far beyond what is visible. The Oort Cloud occupies a similar role in extending the perceived structure of the solar system. The concept of the Oort Cloud also strengthened the view that star systems interact continuously with their galactic environment. The Sun is not an isolated object moving through empty space. It carries with it an enormous gravitational domain shaped by the surrounding galaxy. Through these changes in perspective, the Oort Cloud permanently altered the way the solar system is defined. It transformed a once compact picture into a vast, layered structure whose most distant components remain unseen, yet scientifically essential. Observations of distant star systems indicate that the presence of structures similar to the Oort Cloud is likely a common outcome of planetary formation. When giant planets form around other stars, the same gravitational scattering processes that shaped our own solar system are expected to occur on a broad cosmic scale. Astronomers have detected evidence of distant debris reservoirs around other stars through infrared observations. These observations reveal faint halos of cold material extending far beyond the main planetary regions. Although individual icy bodies cannot be imaged directly, the thermal signature of large populations of frozen debris suggests the existence of Oort-like clouds around many stars. Computer simulations of planetary system evolution consistently produce such distant reservoirs when massive planets are present. These models show that early gravitational interactions naturally scatter icy material outward, forming spherical comet clouds over time. The process does not require special conditions unique to the Sunday. The apparent universality of Oort-like structures suggests that long-period comets may be common throughout the galaxy. Many star systems may possess their own distant sources of cometary material, capable of delivering icy bodies toward their inner planets under the influence of galactic tides and passing stars. An everyday comparison can be made to cities that independently develop similar outer storage zones as they grow. Although each city has a unique layout, the need to store excess material beyond the central district leads to the repeated formation of remote warehouses. In a similar way, planetary systems appear to repeatedly generate distant comet reservoirs as a natural outcome of their development. The comparison between the Oort Cloud and similar structures in other systems also reinforces the idea that the solar system is not an isolated exception. Its large-scale architecture reflects universal physical processes operating wherever stars and planets form. Through this broader comparison, the Oort Cloud becomes not merely a local feature of our solar system, but part of a common galactic pattern in the formation and long-term evolution of planetary systems. The Oort Cloud is not a permanent structure on cosmic timescales. Its long-term survival is governed by slow gravitational processes that act over hundreds of millions to billions of years. Although it appears stable within human observation, its gradual erosion is inevitable. The primary force responsible for this slow loath is the combined gravitational influence of passing stars and the tidal field of the Milky Way. Each stellar passage slightly reshapes the outermost orbits of the Oort Cloud. Over immense periods of time, these small disturbances accumulate and steadily remove material from the Sun's weak gravitational hold. Some objects are redirected inward and become long-period comets. Others are pushed outward beyond the Sun's influence and are permanently lost to interstellar space. This slow leakage continues without interruption as the solar system travels through the galaxy. The Sun's own evolution will also play a decisive role in the fate of the Oort Cloud. As the Sun ages and eventually enters the later stages of stellar evolution, its mass will change, altering the gravitational strength that binds distant objects. A reduction in solar mass will weaken gravity and accelerate the dispersal of the farthest icy bodies. An everyday comparison can be made to a large reservoir with microscopic leaks along its walls. At any given moment, the water level appears stable. Over long periods of time, however, the slow loss becomes unmistakable. The Oort Cloud undergoes a similar gradual depletion under constant but subtle forces. Numerical simulations indicate that a substantial fraction of the original Oort Cloud population will be removed over the full lifetime of the Sunday. Yet because the initial population is so immense, a large number of objects will likely remain bound for billions of years into the future. The Oort Cloud is therefore best understood as a long-lived but slowly diminishing feature of the solar system. Its persistence reflects the immense scale of gravity and time, while its gradual erosion reveals that no structure, even on the largest scales, remains unchanged indefinitely. The direct exploration of the Oort Cloud remains far beyond the reach of current space missions. Its immense distance places it well outside the operational range of even the fastest spacecraft ever launched. The outermost probes have only begun to enter the transitional region beyond the Kuiper Belt. Present-day spacecraft travel at speeds that would require many thousands of years to approach the inner boundary of the Oort Cloud. Even under ideal conditions, chemical rocket propulsion is insufficient for practical journeys to such distances. Reaching the Oort Cloud would demand propulsion systems far more advanced than those now in routine use. Theoretical designs for future spacecraft include fusion-powered engines, light sail propulsion driven by powerful lasers, and long-duration nuclear systems. These concepts promise much higher speeds than conventional rockets, potentially reducing interstellar-scale travel times by large factors. Yet even with such advances, missions to the Oort Cloud would remain multi-generational undertakings. Robotic exploration would be the first viable approach. Autonomous probes, equipped with long-lived power systems and self-correcting navigation, would be required to survive the extended cruise through deep space. Communication delays at such distances would stretch to months or years, forcing spacecraft to operate with a high degree of independence. An everyday comparison can be made to planning an expedition across an unexplored ocean using early sailing technology. The destination is known in theory, but the journey exceeds the lifespan of the builders. Only long-term design, sustained power, and exceptional navigational stability make such voyages conceivable. Indirect exploration will continue in the near future through improved astronomical surveys. Advanced telescopes will refine measurements of long-period comet origins, allowing increasingly precise reconstruction of the distant reservoir that produces them. This remote sensing will gradually improve the scientific map of the Oort Cloud without physical travel. The first true journey to the Oort Cloud, therefore, belongs to a distant technological future. It represents a boundary not only of space, but of the long-term capabilities of human engineering and endurance. The visible planets occupy only a tiny central region of the solar system when measured against the full scale revealed by the Oort Cloud. The distance from the Sun to the outer planets defines the familiar planetary neighborhood. Yet this region represents only a small fraction of the Sun's true gravitational domain. When the Oort Cloud is included, the solar system expands in scale by tens of thousands of times beyond the orbit of Neptune. The Sun's influence reaches far into interstellar space, forming a vast, spherical, gravitational territory that dwarfs the flat disk of planets, moons, and asteroids. On everyday scales, this difference is difficult to visualize. A useful comparison can be made to a small, illuminated room at the center of an enormous, dark warehouse. The lit room contains all visible activity, while the warehouse itself extends far beyond what the occupants can easily perceive. In the same way, the planetary region sits as a bright inner core within a much larger, mostly invisible, solar structure. Including the Oort Cloud also alters the understanding of how the Sun interacts with the surrounding galaxy. The solar system is not merely a collection of planets in isolation. It carries an extended cloud of debris that responds to both solar and galactic gravity at the same time. This overlapping zone forms a transition between the Sun's private domain and the broader environment of the Milky Way. Astronomical models show that this extended structure plays a role in regulating the long-period comet population that occasionally enters the inner solar system. Without the Oort Cloud, such comets would be exceedingly rare. Its vast size, therefore, directly affects what is observed from Earth. The true size of the solar system, when defined by gravitational influence rather than by visible objects alone, is therefore far larger than early astronomy once assumed. It is a structure whose outer boundaries blend gradually into the galaxy itself. Through the inclusion of the Oort Cloud, the solar system is revealed not as a small planetary arrangement, but as an immense, layered gravitational system occupying a measurable volume of interstellar space. The Oort Cloud represents the outermost known boundary of the solar system, as defined by the Sun's gravitational influence. Beyond this region, objects no longer remain reliably bound to the Sun, and instead drift under the dominant control of the Milky Way's gravity. This boundary is not a physical wall or a visible edge. It is a gradual transition where the Sun's pull weakens until it becomes comparable to the gravitational forces exerted by nearby stars and the general mass of the galaxy. Within this zone, motion is governed by competing influences rather than by a single central source. In practical terms, the Oort Cloud marks the region where the identity of the solar system as a distinct gravitational structure begins to dissolve. Inside the planetary region, all motion is tightly organized around the Sunday. Within the Oort Cloud, this organization becomes diffuse. Beyond it, the Sun is only one gravitational participant among many. The concept of a gravitational frontier also reshapes how isolation and connection are understood in space. The solar system does not exist as a closed island. Its outermost boundary constantly interacts with the surrounding stellar environment through slow gravitational exchange. An everyday comparison can be made to the edge of a country, defined not by a wall, but by a wide borderland where cultures, laws, and influences gradually overlap. The boundary exists, yet it is defined by transition rather than by sharp separation. The Oort Cloud functions in a similar way at the edge of the Sun's domain. At this frontier, the material left over from planetary formation meets the broader flow of interstellar matter. Objects may remain tenuously bound for long periods, or may slowly drift away to become part of the galaxy at large. As the final frontier of the solar system, the Oort Cloud reveals that the Sun's domain fades into the larger structure of the Milky Way through a zone of gradual gravitational exchange rather than through a sudden end.